Now I'd like to show you a couple problems where you're asked to predict the amount of precipitate formed given an excess amount of one of the ions in the precipitate, and then determine the equilibrium concentrations of the constituent ions. So in this case, we have silver chloride as the precipitate forming from 30 mils of 0.025 molar silver nitrate and 50 mils of 3 molar NaCl. So it should be pretty clear that NaCl is in excess with that high molarity of 3 molar. I set up an ICF table, as I did in 151. We're going to treat this formation of the precipitate as a completion reaction like we did in 151. So I converted the volume and molarity information into moles, entered those mole values into the table, and we're going to assume initially that there's no silver remaining, and 7.5 times 10 to the minus fourth moles of the precipitate formed. Converting that mole amount to grams, we answered the first question, which is the amount of grams of precipitate formed, which is 0.107. We deal with the next part using the skills from 152 that we've learned recently. What are the equilibrium concentrations of the silver and the chloride ion? Now we'll use the solubility product constant for silver chloride and set up an ice table to determine the equilibrium concentrations of the remaining ions, the silver and the chloride. Regarding the initial concentrations of the silver and the chloride, we need to determine the molarity of the chloride based on the moles of chloride that remain after the precipitation reaction. 0.149 divided by the new volume, 80 milliliters or 0.08 liters. So determining that new volume is very important to determine the molarity of ion that it remains in excess. And we could assume that the molarity of chloride at equilibrium is 1.86 because of the amount of silver that would form from equilibrium is going to be very small for a couple of reasons. Number one, the solubility of silver chloride is extremely small, but also look what's going on. We have chloride ion remaining at high concentration, a common ion. So we're going to get that common ion effect, essentially pushing the equilibrium backwards regarding forming silver ion. So the amount of silver that's going to form is going to be really small compared to a solution of just pure silver chloride without any common ion. So having the excess here really helps simplify our math. So let's take a look down here in the solubility product expression. Silver is the unknown. It can't be zero, as we assumed initially in our first step for the formation of the precipitation. There has to be something remaining, and that's our unknown, X. And we're assuming the concentration of chloride is 1.86 based on what I said earlier and these statements here. So now our math is pretty easy, and we solve for X, which is the silver ion concentration. And you could see how extremely small this is in the presence of the common ion as compared to what it would have been in pure water without the presence of the common ion. In this problem, there's the formation of silver carbonate from 30 mils of 0.025 silver nitrate and 50 mils of 3 molar sodium carbonate. It's pretty evident the sodium carbonate is in excess, and we'll treat the first part like a Gen Chem 1 151 problem, converting the volume and molarity information to moles and predicting the amount of product that would form in moles in the table. And we're going to initially assume no silver is left, and the gram amount of silver carbonate that is formed is 0.207. So now we'll determine the molar concentrations of the silver and carbonate at equilibrium. To do this, we need to treat this part of the problem like a Gen Chem 2 chemical equilibrium problem. So we need to set up an ice table and look up the solubility product value for silver carbonate. The initial concentration of silver we're assumed to be 0, and the initial concentration of the carbonate we're going to use as the ending concentration from our first part, the amount of excess that remained. Represent the equilibrium concentrations as 2x for silver, and we're going to leave the carbonate concentration as approximately 1.84 because there's going to be such a tiny amount of silver ion that would remain. Substituting the equilibrium concentration values into the KSP expression, for silver it's 2x, so it's 2x squared, and then for carbonate it's 1.84. Solving for x, getting through the math, we find that the silver concentration is 2.14 times 10 to the minus 6th. The concentration of silver, in this case in the presence of carbonate at 1.84 molar, is pretty small compared to the concentration of silver in pure water.